Sometimes you may not care to dovetail your stock. And in other cases, you may want to increase the rigidity of your work holding. Or maybe the stock is just too big for that vise to clamp on. In this video, I'm going to show you how to model a parametric stock body so that you can choose to dovetail it when you would like, or have it automatically dovetail when the stock is too big for your vise. This video will be broken down into 3 sections. First, I'll show you an example of how I use the stock body in an assembly. The second, I'll show you how to draw the stock body. And in the third section, we're going to go over the underlying function so you can understand how it works and how you can change it so it works with your vices. So looking at the assembly here, I'll pull up the right side and you can see that this stock body is not dovetailed. In the event that I want to dovetail it, I would pull up my parameters and change this parameter here, dovetail width, to something like 1 inch. And now you can see that that is dovetailed. In the event that I only want this to dovetail when the stock exceeds the capabilities of the vise, I could put something like my stock is 6 inches. That is larger than this vise can hold on to, and you can see that it's automatically dovetailed. Now, I'll bring you into another part here so we can see how I drew this up. This is the dovetailed stock body at its start, and the first sketch is a simple rectangle with 2 dimensions. The first one is the stock X parameter, and the second one is the stock Y parameter. I then extrude this sketch, and that is the stock Z parameter. So in this case, we have 3 by 3 by 1.5 inches. Now in the next sketch, this is where I draw the dovetail. Now I said earlier that this will only dovetail when the stock exceeds the capabilities of the vise, but that's not necessarily true. There's actually always a dovetail of at least 1/1000ths on either side. And the reason is, if I didn't have a dovetail at all, I would have to create new joints. So I don't want to do that. I don't want the existing joints to break. So I compromise with that 1/1000th dovetail, which shouldn't actually make any difference in reality. And so looking at this sketch, we have the dovetail features modeled on either side. This 1/8 inch dimension right here ensures that when the dovetail is at its smallest, meaning 1/1000th on either side, it doesn't collapse in on itself. And now if we zoom out and take a look at this here, we have the dimension between the dovetails at the shortest point. And then this one is just keeping them centered. This one here actually doesn't have the dovetail width parameter that I showed you previously. This one has a special parameter that references that parameter, as well as the stock size and the vice's capabilities. So I'm now going to pull up an Excel sheet so we can break that down. Now the function that controls the dovetail width is actually a couple of different functions that are used in conjunction with each other to create the result we want. The first of those functions is the minimum function. And the way the minimum function works is it takes in a minimum of 2 values and it outputs the smaller of any of those values. In this case, we have value 1 equals 10, value 2 equals 7, and so it outputs 7. If I were to change this to something like 1, it now outputs 1. The second function that we use is the opposite. It's the maximum function, which works exactly the same, except it outputs the larger of the values. So in this case, we have value 1 equals 20, value 2 equals 60, and so it outputs 60. If I were to change this to something larger than 60, as you might guess, it outputs that value. Now this is actually the full formula that we use when creating the dovetail. It is a minimum function and a maximum function nested within another minimum function. The way this works is just like the ones that we just talked about, except it's going to first calculate this. And in this case, we have 4 and 6. The smaller of the 2 values is 4. And then the maximum value over here, we have 0.5 and 2, so it outputs 2. Now this larger minimum function is going to take these 2 numbers, 4 and 2, and it outputs 2. Now, you don't really need to know what's going on here. This is just an example. So I'm going to pull you over to this tab, which is the dovetail formula and the actual values that we care about and what they're doing. Now what we have here is the minimum function and the maximum function nested within the larger minimum function, exactly like on the previous tab. The main difference is this first minimum function is going to do a little bit of math to calculate the first value. In this case, we're giving it the stock Y dimension and the minimum contact, which is, like I said, when there's no dovetail, there's actually a dovetail of 1/1000th of an inch, and that's where this value comes from. As I put 2/1000s here, and that ensures that we have at least an indentation of 1/1000th on either side of the stock body. So value 1 is calculated from those two values. The second one is our max vise opening. This is our vise's capabilities. So we just hard code that in there depending on whatever vise we're using. Now the maximum function takes in the minimum vise opening. So when you close those jaws all the way, but they're not making contact, so you still have some clamping force, what is that distance? In this case, I'm putting a 1/2 inch. The second value that this takes in is the dovetail width. And this is the value that we manually change when we want to have full control of that dovetail. And the output is going to be the smaller number of these two. In this case, it's 4. I understand that that's probably not the best way to take in this type of information. So I'm going to head back over to Fusion and we're going to look at the assembly once more and pull up those parameters. So as we can see here, I have the dovetail limits do not change, and that is because there's no reason to change it once you have it set up properly for your vise. In this case, we have the minimum function, and within that minimum is our first minimum function and then our maximum function, just like we had in the Excel sheet. Now we have the stock Y dimension that's being taken from this parameter minus 2,000. So the largest it can be, and then subtract 2,000 so that we are engaged in that material. The second value, I put 3. That is the max capabilities of this 5th axis vise. Now the second value that we're pulling from this minimum is the maximum function. So we have a 1/2 inch. That's the minimum that I think that this vise can close and still maintain clamping force. And the final value is the dovetail width, which we control here. Now, one more example, I'll just show you all the different ways that I can control this. So again, if I switch this to 2, we have no dovetail. If I want a dovetail for any reason, I can then manually change that there. If this value here is larger than or equal to the vise's max capability, it will default to the smaller of the two. So if I change this stock Y dimension to be something like 4, which is greater than the 3 that we input right here, then you can see that it automatically dovetails. Now, I sort of stumbled upon this by accident when trying to make this like foolproof assembly for a client where I didn't want the joints to break under any conditions. And what ended up happening was the stock dovetailed itself when you made the stock bigger than the vise could hold on to. And so I just wanted to share that with you. If you have any other questions after watching this video, please just reach out to me. This topic seems a little bit dense to be talking about in a video, a little bit boring, and maybe hard to understand if it's your first time looking at these things. So yeah, reach out to me if you have any questions, and I'd love to help you.